Okay, welcome to EE222. Last week, let's have a look at what we were doing last week. It's week 1, week 4 and 5. We are now on week 6, by the way. Some of you have started lab 3, some of you will be doing lab 3 later on. Okay, yeah, we were looking at building gates of different sizes. Remember, as I've always mentioned, when I write in the exercise book, that's only I'm only attempting to give you some extra examples. I'm only attempting to give you some extra examples, but the main notes is still on the Moodle shell. All right. Okay, so these are some very basic how to build some gates again in the particular thing, in the particular you would call it lab. You are building some more gates, so you just got to have an idea. Now, the two keywords which I introduced to you last week was something known as a nan-nan realization, and there is the counterpart for nan-nan is no-no. So if you go back, if we roll back to week 4, somewhere around there, week 4, beginning of week 5, I showed you, hey, you can build AND gate, NOT gate, OR gate, XOR gate, all using AND, or if you want, you can build it all using NO. So NO gate and the alternative is NAND gate are known as universal gates, and you can build all the basic logic gates, whether it's AND, NOT, OR, XOR, XNOR, all using the universal gates. If you can build all the basic gates with universal gates, you can then build large circuits using universal gates, right? And I've given, so basically this is an example here. They have this circuit, the original circuit, and what they've done is they've gone and converted that original circuit into a nan-nan formation. So sometimes I might give you a problem, right? There might be a problem given. Right, let's have a look at one of last week's problems. There was a problem given, and the problem was we were to build an absolute, you're required to build an absolute one majority detector, right? Okay, majority detector for the case where output is, where inputs are 1. So we went through the truth table, we found the outputs. Then we brought out the sum of products algebraic function. We brought out the sum of products function in terms of, in the expression as a sum of min-term expression. So both are sum of products. One is written as an algebraic function, one is written as a sum of min-term expression. Then we looked at the AND/OR circuit. I said, hey, that's part of your homework. Then I said, okay, there's a product of sums as an algebraic function. So sometimes when, sometimes the specification will be, could you draw this, could you write it out as a product of sums in algebraic format? Then there is a product of sums as a max term expressions. Then there was a OR-AND circuits. Obviously, if it's product of sums, it will be OR-AND. Then I said, hey, convert that into a nan-nan. Convert that into a nan-nan and nan-nan, and the other one was no-no. All right, so I gave you a bit of homework, and make sure you guys have attempted that honestly, because you will be receiving something like that in your midterm exam. All right, now let's move on to the next topic, guys. Let's move on to the next topic. So this was some examples I gave you. I said, hey, you can build a 4-input OR gate using a 2-input OR gate, right? And please take note of earlier examples. I said there's XOR. The way of converting the XOR into nan-nan, and then I gave you an alternative circuit as well for XOR. Okay, and I said make sure you draw the truth tables and all that. So whenever I give you some problem, that's obviously I'm giving you some extra task which is directly related to our test or quiz or something along those lines. Right. Now, for today, I want to introduce you to a particular new topic. A new tool. Okay, so today's date is, can somebody help me with the date? 20, and this is week 6, lecture 1. All right, fair enough. Okay, now the new topic is, and you will see it over here, Carnot maps. Okay, remember this name. It's called Carnot maps. I'm not sure if you guys attempted Carnot maps in CS211. Carnot maps, okay. So I think now you will start to see that CS211 and EE222 start to diverge, right? CS211 would still stay on the soft side. We will go deeper and deeper into analysis. So a new topic called Carnot maps. All right. Now, what are we doing here with Carnot maps? So let me just write that out. K maps. That is the new topic. All right, guys. Okay. Now, a Carnot map is another tool. So what we've been doing now is when you've given a very large an expression, one way to reduce it is what? What is the first way? If I give you a Boolean expression and I say, can you reduce this please can you minimize this? The word is minimize. Can you minimize this? So what do we use? What tools do we use? All the theorems, right? All the theorems, we use our 13 theorems to reduce it or to minimize it, right? Now, Carnot maps is a tool, another tool. So basically, from the beginning of this course, I've been equipping you with two things. I've been feeding you with basic building blocks. What are the basic building blocks? I said, okay, this is a NOT gate, this is an AND gate, this is an OR gate, right? These are basic building blocks. This is how it will function, right? Then I said, okay, this is a NAND gate and it can also be used as a universal gate. So I taught you some things. So in your toolbox, you are continually filling your toolbox. Then I said, hey, these are some new tools, 13 theorems with which you can reduce and minimize these long Boolean algebraic functions. Then I gave you, okay, there is another tool called sum of products or product of sums. And the idea between sum of products and product of sums is it brings it into 2 layers or 2 levels. Now this is another tool. So as we go along, you'll be learning newer and newer tools, and at some point in time, you will then start to apply the tools. Apply it to realize something stick, right? Like for example, a traffic light system, a vending machine system, a pin code detector system. These are all real life applications. But you can't get from zero to something big like that straight away. You have to have the basic essential tools. So this is another tool for the purpose of minimization, right? What is the purpose application? It is minimization. And it brings it into like not a sum of products or product of sums, but you can feed sum of products and product of sums, like for example, that example which we did the other day with the majority 1 detector, absolute majority 1 detector, right? Some of the product of sums would have been very, very long, right? You've got to minimize that. That's not the real minimize function. So how do we minimize? Well, 2 approaches. You can minimize using your 13 theorems, or we can apply K-maps. So let's start off with some examples. And by the way, if you don't understand me, you can always look this up, all right? You can always look it up. Okay. I'm going to flip over to the document camera. Okay, let us consider the following truth table. So, 2 variable. So this is 2 variable K-map. Okay. Let us consider this following truth table. I don't know, it may be, and our output is X. 0, 0, 0, 1, 1, 0, 1, 1. Okay, so 2 inputs, so obviously there will be 4 possible outputs. 2 inputs, so obviously there will be 4 possible outputs. Okay, now let's just put some populated with this thing here, 0, 1, 1, 0. Okay, so that's our outputs. Now, okay. What is the K-map? This is our truth table. On the left hand side we see a truth table. There is a truth table of a system, of a 2 input system, 2 input single output system, double input single output. Now a K-map is another way of drawing the truth table but in a 3D way. Okay, now a K-map, when you look at a truth table, so all I'm trying to say over here is our truth table is a table and it just keeps on going downwards. Right? If you have more data, you keep on going downwards. With K-map, it is the same data but it goes in a 3-dimensional, it extends out 2-dimensionally, or sometimes even you can go take it into 3-dimensional. Alright, so these are the inputs. A, B, right? Okay, so what I'm drawing is, this is truth table, this is Carnot map. Basically, I'm transforming this into Carnot map format. So maybe think of it like this, guys. If you remember again drawing, when you were doing some drawing in secondary school, you can draw a chair in isometric view, or you can draw the same chair in orthographic view. They're the same thing. It's only different format. Okay, so that's what we are doing. Truth table and Carnot map are the same system. They're referring to the same system, but it is being drawn in a different way. Okay, now. Okay, so over here, look at the labeling 0, 1, 0, 1. Right? So what we've done is we've brought it into this box or 2-dimensional 2 by 2 sort of format. So if A is 0, what do you call this, guys? What can we call this? This would be known as A bar. And if A is 1, that would be A. So this row over here is all related to A. This would be B bar. This would be B. Right? Okay. Everyone all right there? Okay, now we label the cells. Can you see these four windows? The 4 windows. We call those windows the cells, the Carnot map cells. So those Carnot map cells have addresses. Oh, wow. Addresses. That sounds familiar. The word addresses sounds familiar, right? Remember when we were doing the truth table and we were looking at sum of products and product of sums, we were also talking about addresses. So what was this line address number? 0, 1, 2, 3. How did we find these numbers? 0, 0 is 0, 0, 1 is 1, 1, 0 is 2, 1, 1 is 3, right? Remember when we were talking about those addresses. And where did this 0, 1, 2, 3 go and plug in? Into the sum of products and product of expressions. So let's just quickly do it. So if this was if we wanted to represent this particular truth table as a sum of min-term expression, what addresses would be listed? 1 and 2, yeah? Okay, so remember those words, addresses. So this is where they all tie in. Just like, again, example is, I'm sorry for the guys who did biology and who probably didn't do drawing in secondary school. But yeah, this is a very good example. Whether you draw the chair, how many of you guys did not do drawing? Okay, all right, so you may have seen, well, but even then, I believe you've done a little bit of MM101, right? I think that's core for everybody, yeah? It's a core course. So whether you draw the chair or the table in isometric or oblique or orthographic, the dimensions will still be the same. The dimensions, because you're still referring to the same system, the same object. So these addresses will also transfer to here, right? And sum of min terms, product of sums, product of mixed terms expressions, all that will tie in. Everything is linked together. It's only different formats. Okay? Alright, so, but this format has its advantages. I'll show you shortly. This format here has its advantages in the sense of that it is very nice to extract your sum of product expression or product of sums. This format here is better for minimization. Everybody has its own advantages. So okay, 0, 0, we call this cell number 0. All right, 0, 1, we call this cell number 1. So I'm writing this cell number over here, or the cell address. 1, 0 is cell number 2, 1, 1 is cell number 3. All right, cell address 3. Okay, so those are our cell addresses. Very straightforward. Right in the beginning, I'm writing those cell addresses out because I'm teaching you. Later on, as you become more confident and as you become a pro in handling Kano maps, you don't need to write down the cell numbers as you become more confident. All right. Okay. It's only in the beginning, just like over here. Right in the beginning, I'm telling you, oh, this is line address 0, line address 1, 2, and 3. I'm just writing this here for the purpose of teaching. But in reality, we don't need to write this down because as you become confident, you don't need to write the address down. You'll be able to pick it up itself. All right? Okay. Now, let's fill that Kano map up. That Kano map is still empty. All I've done is I've drawn the Kano map. I've labeled the axis. I've labeled the A axis, the B axis, or the A input, the B input. I've said where the 0, when A is 0, that's sort of talking about when A, you don't need to write 0 and A bar. You just write 0, that's good enough. That will tell you that, okay, that's A is, in that line is 0, which means it's A bar, right? Okay, so now let's populate it. Let's fill the Kano map up. So, when A was 0 and B was 0, what was X? 0. When A was 1 and B was 0, A was 1, B was 0, X was 1, right? When A was 0 and B was 1, A was 0 and B was 1, X was 1. When A was 1 and B was 1, A was 1, B was 1, X was 0. So do you see, it is the same thing. All we've done is, we've taken our truth table and just redrawn it in a 2 by 2 manner. Rather than heading downwards, we've gone in this direction. Okay? All right. Let us now consider another example. Okay, let's consider C, D, and let's consider Y. Automatically, you should remember, if there's 2 inputs, how many possible combinations for outputs, guys? 4. Yes. 0, 0, 0, 1, 1, 0, 1, 1. Let me populate the output in terms of blue color. Put C there. D 0, 1, 0, 1. Just to explain to you guys, you don't need to write the C bar up, but I'm just doing it to show you that when D is 0, that's D bar, and when D is 1, that's D, right? So everything going in that direction. So you have to look at it from a graph point of view. All right, now let's now fill this up. Oh, let's do the addressing. 0, 1, 0, 0 is 0, 0, 1 is 1. 1, 0 is 2, 3, all right? Now, 0, 0 is 1, 0, 1 is 1, 1, 0 is 0, okay, all right? Okay, now, here's the catch. So is everybody in agreement with me up till this point in time? So, up till now, you've been seeing that Kano map is just another way of redrawing it. Now I show you the application of Kano map. Check this out. Check this out, all right? These 2 1s are sitting beside each other. How many of you guys have done Kano maps in ME161? Nobody's seen this before. Okay, right. So, check this out. These two ones are sitting beside each other. So we group them. All right. Now there will be some rules about the groups, and I'll explain that to you shortly. The groups can be made only in powers of 2. Only in powers of 2. What do I mean? So a group can be of 1, 1. Oh, firstly, you only group the ones. Now, I want you to recall ones. When we talk about ones as the output on a truth table, what are we referring to? It comes from last week, guys. Sum of products. Yeah? So obviously, when we are grouping the ones over here, remember the ones over here are the ones here. Yeah? Okay? When we are grouping the ones, what are we grouping? The sum of products. All right. Now, grouping is easy. So groups, firstly, rule number 1, you can note this down. You only group the ones, right? Rule number 2, you group in groups of, you group in powers of 2. So 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. You can't group 3 ones together. Why? Because 3 ones sitting in a line, they don't make a power of 2. So the group has to be, the size of the group has got to be 1, 1, or 2 ones, or 4 ones, or 8 ones, or 16 ones, or something like that. Right? Okay, powers of 2. Remember that. Right? And the other thing is, they've got to be either horizontally neighboring each other or vertically neighboring each other. Right? Can't do diagonally. Okay? So they've got to be sitting beside each other horizontally or vertically. All right. So I'll show you more examples. Now, I've grouped that one. Have a look here, guys. This is the important part. Pay attention. Everybody's happy with this group? Everybody's happy? Is everyone happy with how I got from the truth table to the Kano map? Mapping, that's quite straightforward. Grouping, we'll get more practice on it, but this is the actual application. The output is equal to y. The output was y. Right? And what do we say? We say y is equal, look at the group. The group occupies which column? C bar. So y is equal to C bar. That whole function is minimized, is now minimized in minimum sum of products. You call this MSOP. Right? Okay, where did the SOP come from? Why is it SOP? Because we are grouping the ones. Right? So therefore, when we did the grouping and we found out, hey, this group is occupied by that whole row, right? Yeah, that whole column, which is C bar. So, see, C bar. So y is equal to C bar. And this here is the minimum sum of products. Right, let's look at another example. I'm going to flip the page. Let's take it up. Let's look at 3 variable. Let's look at the 3 variable Kano map. All right, let's consider A, B, C, zero, 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 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, and let's just put some numbers there, guys. Just put some numbers. 1, 0, 1, 1, 0, 1, 0, 1. All right. Okay, let's now try and draw this Kano map. Obviously, you've got 3 inputs now. You've got 3 inputs. Okay, fine. 3 inputs. The Kano map will look like, or can look like something like this. You can put A, B there. You can put C there. Right? So you call this Carnot map a 3-variable Carnot map. Right? 0, 0, 0, 1, 0, 1. Right? Obviously that means that that's C bar, that's C. Right? The catch with 3-variable Carnot maps. This is the tricky part. The tricky part wasn't the group. The tricky part is in the labeling. The moment you have Carnot map whereby your third column, right, the moment you have a Carnot map whereby it's more than 2 variables. The first example, example 1, example 2, there were only 2 variables, 2 input variables, input A, input B. In this case, there's input A, B, C. So obviously to entertain the extra input variable, we have to have 2 inputs on this side, right? Okay, so one axis occupies 2 inputs, another axis occupies another input. Now look at the labeling here, guys. Look at the labeling. 0, 0, 0, 1. A lot of you would think of this as what? Naturally you would think as 1, 0. But actually your 1, 0 is there. Okay? This is the convention of the Carnot map. Now, the way to think of the Carnot map is that it is like a ball or a sphere. It is connected, right? So your sphere from this side can also loop on that side. I'll show you more about this. Okay. All right. Let's do the. So the important thing to note, maybe you jot it down in your exercise book. Note that 1, 1. It's 0, 0, 0, 1, then 1, 1, then 1, 0. Okay? All right. Now, 0, 0, 0, cell number 0. 0, 0, 0 is cell number 1. 0, 1, 0, cell number 2. 0, 1, 1, cell number 3. Look at me. I jumped to this line here. 1, 0, 0 is cell number 4. 1, 0, 1, cell number 5. 1, 1, 0, cell number 6. 1, 1, 1, cell number 7. All right? Okay. Now, A bar, B bar, A bar, B, A, B, A, B bar. All right, let's fill it up. Oh, let's put some address lines over here. That was 0, 1, 2, 3, 4, 5, 6, 7. All right. So 0, 0, 0, 0, 0, 0. X is 1. Okay. 0, 0, 1 is 0, 0, 1. 0, 0, 1 is 0. So we can, another technique I want to show here. There's a lot of things which tie in, which makes life easier. If you know your address number in the truth table and you know the address number of your cells, they are the same thing because all you're doing is you've drawn it in a different way. So you can just copy off cell 2, line address 2 is same as cell 2, 1, 3, 1, 4 is here, 0, 5, 1, 6, 0, 7, 1. Okay. Right? So we've populated the truth table. So the first thing is we drew the truth table, then we populated it, and it was easy to populate because we know the line addresses here and the cell addresses are the same thing, they match. Okay. Now we draw the grouping. So 4 steps. Draw. Step 1 is draw. Step 2, populate. Step 3, group. That's group. What can we do about this guy? Group of 2, right? Okay. What can we do about these 3 over here? Can we group the 3 all one shot? No, because 3 is not a power of 2. You can either group as 2 to the power of 0, 2 to the power of 1, 2 to the power of 3, 2 to the power of 4, and so forth. So, what is the next possible group, guys? How about we group this way? And then you have last one left, all the ones must be grouped. All the ones must be grouped. Okay? So you've got one more one left. So the way to do it is, we don't group him alone. We try to make, another objective is, the groups must be as large as possible. As large as possible. Can we make a group of 3? No. The next possible option is group of 2. Okay. Let's consider this first group, guys. Pay attention over here. Let's consider the first group. You don't need to look at the truth table anymore. It's all about the Carnot map now. Okay. Once your information has gone from the truth table into the Carnot map, from there it's about grouping and then getting the function. Right, so x is equal to, let's look at the first one. The first one is, what can you say about this guy? What line is it in? In the horizontal C bar, right? C bar, and I'm talking about this first group here, guys. C bar, and what can you tell me about this thing here? C bar, what is common between these two? A bar is common, not B, because B is B bar over here and B over here. So we say A bar, C bar. All right, A bar and C bar. Then you put an O. Then you put in O. All right, let's look at the second group. Second group, there will be C, and what's common? B. Right? Let's look at this third group. What's common? C on this on the horizontal front. Vertically, if you look at the columns, A. So what we can say is, this guy here, that's coming from this one. This fellow here comes from this guy. This guy here comes from that guy. So 3 groups. Every group gives us what? What do you call this guy? One of this, when you write out an expression, what? Min-term. Every group is a min-term. So you see how sum of products, the min-term, sum of min-term expression, product of sums, all those things, right? The line addressing system, cell address, they all tie in together now. This here is not a sum of products expression. It is a minimized sum of products expression, right? So if we were to, let's just go up just for a second. If I were to say, hey, can you find me the sum of products expression for this? So what would it be? Let's do that one now. There will be A bar, B bar, C bar. Next one. There will be A bar, B, C bar. Next one. A bar, B, C. A, B bar, C. A, B, C. So what we have over here is, we could say that x in the sum of products expression would be equal to A bar, B bar, C bar, or A bar, B, C bar, or A bar, B and C, or A and B bar and C, or A and B and C. Set. And when we say the minimum sum of products expression is equal to can you see the difference between the two? And there's another one. What's another one which you missed out? X of A, B, C is equal to sum of min-terms, open bracket, 0, 2, 3, 5, 7. I want you to note the difference between the group, 3 different things which you've done. The sum of products expression, directly extracted from the truth table, very, very long. The sum of min-term expression only gives the addresses of where the what is located. Ones are located, right? Funny thing, in our Kano map, we are also mapping, we are grouping what? Ones. The minimum sum of product expression, where did this come from? The Kano map. We group the Kano maps, and if you group it rightly, you will get the right answer. Right? Okay. Now, what would have been another way to go from here to here? Using your 13 theorems, doing some Boolean reduction. Right? Now, another question. Some would have said, why, look at this second group. Look at this second group. Some people would have said, why did we group these two? Why couldn't we group those two? Yes, the answer is true. You can. Right? You can group it. You can group those two and don't group those two. Okay? So you will have some different possible answers. When it comes to your minimize, this answer is fixed. This answer is fixed. This answer is fixed. Your sum of products expression and your sum of min-term expression is fixed. There's no movement. Your minimum sum of products, yes, there is room for movement. You can have 2 or 3 different minimum sum of product expression, but they will give the same output when you draw the truth table. All right? Okay. So if we would have, let us say, grouped, I'm just going to do it in dotted line over here. If I would have grouped those two, then your minimum sum of products would have been A is equals to A bar C bar. Okay, that line would have been common. This one would have been still been there, AC. What would have changed? Instead of this two, we would have taken this two, right? So that would have been what, guys? A bar B. All right. Let's do another problem. Let's do another problem. Let's switch back to a 2-variable Kano map once again. Let's do, what example was this, guys? Example 3. All right. Now, so let's do some, let's call another one over here. Let's call this F. All right, so let's quickly do this, guys. Okay, let's do X first. I'm going to quickly do some of these ones so that you guys have an idea. A, B, 0, 1, 0, 1. Now, I'm not going to label all of them. I'm going to leave some things out. Your cell addressing, you've got to do on your own. All right? Okay, so certain things I'm not doing over here, but I'm expecting that you will doing it. So I'm going to do the first one for you. Zero, 0 is 0, 0, 1 is 1, 1, 0 is 2, 3. Right? Okay, now 0, 1, 0, 1. Let's look at X. There'll be 0, maybe I should use black, eh? 0, 1, 0, 1. So, what do? We group that together. What can you tell me about X, guys? X is equal to? What is common? Is equal to? B. Right, let's look at the next one. Y. Okay, this time around, I want you to do your labeling yourself. The only way to learn this is by practice, but it's a very important tool. Notice how I'm not labeling all the cell windows this time. So for y, it'll be 1, 0, 0, 0. What do we get? That is a 1. So what do we say? Y will equal to, there's only 1, 1. What do we say? What can we say? Y is equal to, so that's group of 1, which is still valid. Is that a valid group? Yes, because 1 is 2 to the power of 0. So we have A bar and B bar. All right, let's look at another one. Let's look at F. Okay, F, you have 0 and then followed by 1s, right? The truth table is on the top, 0 followed by 1s. Wow, this one slightly tricky. Well, that's a group of 2 over here, and that's a group of 2 here. So what can we say about F? F is equal to, what about this line here? That's A bar, that's A. So that line there will be A. Next group, F is equals to A or B. Right? And if you look at it, guys, let's have a look. Let me show you something. If you look at F, A, B, forget about these 2 columns. Look at the output F. Isn't that the truth table of an OR gate? Yeah, so that confirms it. Okay, let's look at some examples on a 3 variable before we knock off. A, B, C, X, Y, Z. Okay, let's put some outputs over there. Notice how I've used this letter X. I'll show you what that X stands for. That's another new thing, another new item. Okay, so let's just put some address numbers over here. There will be address 0, 1, 2, 3, 4, 5, 6, 7. Let's do X first. Right? Now let's call X. Let's write out X in terms of sum of min-term expression. Sum of min-term expression, where are the ones in X? Where are the ones in X? Guys? In the column X, there'll be 0, 2, 3, 5, 7. I think we just did this early on, right? Okay. Now, the answer, so I don't need to spend too much time on that. It's identical to the problem early on, is it? Okay, so you look for where the addresses are. All right, so let me 0, 1, 2, 3, 4, 5. Oh, sorry, even I made that mistake. 4, 5, 6, 7. All right, notice how the things are labeled. All right, okay, so we now go and find these addresses 0, 2, 3, 5, 7. See how I populated my truth table only using the line addresses. So from here, I was able to jump to here. The rest is quite straightforward. One group here, another group here, another group here. So we end up with x is equals to A bar, C bar, or B, C, or A, C. I think that's the same problem from what we've done earlier on, right? Okay, let's look at y before we leave. Let's make a dash for y. What will y equal to? Y will equal to y in terms of A, B, and C is equals to sum of min terms. Can you tell me the min terms of y? Look at column y. There will be 2, 6, and 7. And then the one with the x is called a don't care. A don't care. And that's located at 3. Right, that's located at 3. Now, a don't care is, let me explain to you what a don't care is. A don't care I want you to consider this particular circuit, AND gate. One input is 0, another input is B. Right? What will be the output of this circuit? It's an AND gate. One of the inputs is 0. What will be the output of this circuit? 0. Why? Yeah, one of the inputs is 0. So B becomes a don't care. No matter what input you supply, whether you apply a 1 or a 0 to B, your output will always remain a 0. That's what you mean by don't care. Don't care is an input which does not affect the output. You can write that down, all right? Don't care is an input which does not affect the output. So B does not affect the system. Therefore, B is a X, which means don't care. It's a very good name, you know. Like this particular circuit, this particular course has got some very good psychological information. So if you have an ex-girlfriend, it should be a don't care value. All right? Okay? So I think a lot of you guys don't have ex-girlfriends. I don't know to be happy or sad for you guys. Okay. All right. That's it for today. We'll continue tomorrow.